is our afternoon session. Thank you all for being with us. I hope you enjoyed the food quite much. You guys are going to hear now two more talks before we have the advanced breakout session. First talk is by Dung. We're going to talk about modeling electrodynamics and nonlinear phenomena in superconducting quantum devices. Currently PhD student in the quantum engineering group advised by Professor Hakan Kurechi, who gave a talk in the morning in the beginner track, which again is recorded, so you can also see his point on it. And then after this, we're going to hear from the Paul brothers. We're going to talk about the field of photonic integration device. With that, please thank the speaker. Welcome, speaker.
Yeah, so thank you for the introduction and for the opportunity to be part of this very nice workshop. And as a member of the audience since yesterday, I've also learned a lot from just the, listening to the lectures and doing the demos. So yeah, this talk will sort of be a slight gear change towards something that's slightly more basic and more heavy on the simulation side. And this is also like a project that's sort of slowly graduating from the proof of concept stage towards hopefully production. And so yeah, I'll be discussing an effort or a general program in broad sense for the E&M modeling of superconducting materials with a focus on capturing the nonlinear interaction of the materials with electromagnetic field. And I will then try to discuss a theoretical and computational framework that we believe could help resolve some of the existing modeling challenges. Right, so, why another modeling method in another toolbox, right? Because, we all know that the community already comes up with, it's really so rich with various methods to model quantum devices. And these methods have, already done a great job of, covering the necessary aspects of, when it comes to modeling quantum devices, right? But it turns out, even though there have been a lot of development on the theoretical approaches and, tools, that results in some, very successful tools that techniques, and many of which we've learned in this workshop. For example, we have, such as AWS Palace or ANSYS HFSS for the classical E&M simulations, or PyEPR, which is sort of like a classical quantum hybrid analysis tool, and SC-qubits from Jens for circuit level quantization analysis. We sort of already see like a, general strategy or workflow for modeling and designing superconducting circuits from classical E&M to quantization. But we feel that there are still, issues or open questions that sort of, prevent accuracy when, especially when devices are becoming, increasingly more sophisticated. And my motivation today is just to try to convince you that there's, or, come up, introduce a way to sort of complement these existing modeling tools by providing something that fills in like the gaps between these techniques. And so the goal or some of the issues that we hope to tackle with our scheme include, first of all, of course, we'd like to model nonlinear transient dynamics in devices. And this could be anything, for example, the response of the materials to traveling microwave pulses, or dynamics of vortices in quasiparticles, and all of which are nonlinear behaviors, processes happening inside the materials, and requires to go beyond the typical linear London boundary conditions or the perfect conducting boundary condition during standard E&M modeling, and because they only capture sort of like the linear responses of the superconductor, right? And secondly, we want to explicitly address input-output losses. And these are, of course, radiative losses due to coupling to the external environment, as illustrated in this diagram here. When you communicate with the outside world, either deliberately through control and readout lines, or unwanted interactions due to improper shielding or packaging, right? And for qubit-like modes, these radiative losses directly translate to precise modification or of lifetimes, which is always an important problem. And yeah, so therefore, we'd like to sort of try to rigorously extend the existing approaches and tools to open systems. And it sort of requires like a spectral theory that I will elaborate later for superconducting devices that sort of incorporate correct open boundary conditions. And beside radiative losses, we also have absorption losses that comes from heating or quasi-particle dynamics, which is also a major concern and cannot be captured just by considering a superconductor as a perfect conductor or a linear material. And yeah, there's also the issue with crosstalks, which can be due to hybridization of modes or unwanted nonlinear coupling due to transient migrations of charges and currents on your device during real-time operations, or flux bias line, for example, of one qubit affects another neighboring qubit. These are some of the examples of crosstalks. And finally, you want to dissect how packaging can affect on-chip operations. So like out-of-plane modes or effects due to the fact that the chip is typically, of course, encased inside a macroscopic box that has its own modes that can interact or hybridize with on-chip modes that modify how your qubit operate, or normal operations of the qubit. Yeah, so those are all really lofty goals, but how do we actually realize them? And we sort of need a formulation that captures the properties of superconducting materials as well, at well below critical temperatures, because that's where the regime that the device typically operate. We also want to study dynamics and evolution of the condensate, superconducting condensate, which is a charged quantum fluid by nature, and not the diffusion of the charge to steady state. We want to study the actual dynamics. And the formulation, however, has to also be robust enough to sort of be applied to complex geometry that contains multiple materials and device components. And moreover, the device will most likely also will also contain non-simplicial topology, right? Because, for example, the transmon qubit, which has a Josephson junction loop, is already like a very simple example of a non-trivial topology. And any theoretical attempt to sort of probe into the superconducting nature of the material will bring into picture the sort of like superconducting phase parameter, which is not a gauge invariant quantity and has to be handled properly, especially when the device contains loops, as in our qubit chips. And right, so thirdly, we would want a formulation that has to be economical enough because we are dealing with superconductivity on a very macroscopic scale, right? So just straight up applying the BCS theory for superconductivity to a full chip containing billions and billions of Cooper pairs is, at least to me, borderline science fiction from a practical point of view, right? Just don't quote me on like the 10 to the 16. I just did a really quick calculation to estimate how many Cooper pairs in your chip. It's just like it is a very big number, and you don't want to simulate that full thing. But you want to capture the gist of it. So sort of like taking all this into consideration, a starting point that we felt is effective is sort of like an effective field theory, which we call the electrohydrodynamics of superconductors, that essentially just couples Maxwell's electrodynamics with the order parameter equations describing the superconducting condensate. And here A and V are just the usual scalar and vector potential, and psi here is the macroscopic order parameter that can be thought of as the wave function of the entire collective condensate as a whole in the device. And this sort of like semi-classical combination, semi-classical because you still use Maxwell's electrodynamics to describe the materials, to describe the light part, but already sort of like step your foot into the quantum regime by employing a Schrodinger-like equation to describe the macroscopic condensate. This allows us to sort of like properly describe radiations at the same time, sort of like peek into the nonlinear dynamics in the material. So sort of checks all the boxes. Yeah, so instead of considering light and matter as interacting with separate entities, we opt to describe them as hybrid objects. hence the introduction of the hybridized field, which is this curly A there. That sort of contains the light component as well as the phase data of the order parameter. And this has two major advantages. First, the theory sort of becomes manifestly gauge invariant and suitable for second quantization, and you can very conveniently address non-simplicial topologies appearing in your devices. And secondly, the hybridized fields now sort of like permeate all of space, not just in the materials or not just in the vacuum, but just everywhere. And it's sort of like from a modeling point of view, it greatly simplifies boundary conditions at material interfaces when you do simulations. Right. So yeah, so beside the sort of like need for choosing a suitable formulation for subconductivity that sort of can capture crosstalks, correlated noises, and hybridization, another major challenge in modeling electrodynamics of circuits, it's that I'm sure everyone that has to actually run the simulation will know when resonate is that it's just the multi-scale nature of the device, right? It's because you have feature sizes ranging from nanoscale, being the junctions, all the way to millimeters and up to centimeters if you try to take into account the packaging case altogether. So a full E&M simulation of such a device, let alone trying to incorporate the nonlinear behaviors, it's just ridiculously prohibitively expensive. Even when adaptive meshing are employed in many of these advanced simulation tools, as in HFSS or even PALIS, are employed to avoid unnecessary overmeshing. It's still a very big task to try to do just a simulation of the thing. So, so the goal here is to sort of like have a very general strategy to sort of address all these challenges and implement them as software packages for quantum electrodynamic simulators. That is about spatial and temporal coarse graining of that I would elaborate later what coarse graining means, to sort of like eventually develop a effective quantum models or model reduction of E&M degrees of freedom outside the computational domain that we're interested in. Right, so a shift in philosophy that we'd like to propose and we've found to be very fruitful in modeling is be working with coarse-grained variables. And this is done through a mathematical techniques called discrete exterior calculus, or DEC, that sort of allows you to sort of reformulate the nonlinear problem into one that is suitable for discrete spaces, such as a finite element mesh, at the same time preserving the structure of the original equations and by automatically enforcing conservation laws. In our case, that would be charge conservations and current charge continuity and also energy conservations. And by enforcing this, you have a theory for the discrete spaces that respects the original equations of motions. And I will not bore you with the nitty-gritty of how to actually do this, but I will show you the key features. And if you're interested, you can just read the papers. So first of all, the formulation sort of employs a dual mesh construction, which is slightly different from standard finite element analysis. Here the dual mesh sort of interweaves into the primal mesh, and is where the material properties are encoded. Simultaneously, we have the primal mesh that carries the field, and it's where the calculations are carried out. You then introduce this sort of like coarse-grained variables, which are living on the discretized mesh of the system during after this mesh mesh generation of your model. For example, a vectorial quantity like the A field would be mapped onto the discrete spaces by performing short integrals across the small discrete edges of your finite element meshes. And the scalar field would be mapped which in our case would be, for example, the charge density will be mapped onto vertices of the mesh by integral over the dual volume that sort of surrounds the dual volume cell that surrounds your vertices. You can then derive during DEC, derive the exact equations for these new cosine variables that describes the electrodynamics of the discrete spaces based on the original equation of motion that I mentioned earlier. And just to note that this is sort of like distinct from my finite element analysis, which is a technique that's widely used and have been very successful, of course. The key difference here is that we sort of simulate the exact dynamics of coarse-grained variables, in contrast to try to approximate the dynamics of continuous variables during your simulations. So it's like this slight change in how you think about this. And it's known that DEC gives you accurate long-time simulations of nonlinear PDEs, which is kind of nice, as shown in the case of the Navier-Stokes equations in fluid dynamics, or in our case, the Maxwell-Schrodinger equations. Right, so at this point, you might also want to ask, why taking the this different route and work with this sort of like rather exotic DEC formulation? And first of all, that's because the equations we tackle are highly nonlinear, and this is very suitable for that kind of problems. And second of all, it more philosophically, if you will, it's because discrete exterior calculus directly deals with coarse-grained variables. And in the QED of superconducting circuits, only the hybridized coarse-grained fields matter. And let me just elaborate on that, right? Because at the heart of any superconducting quantum circuit are the Josephson junctions, which are the nonlinear oscillators, right? Whose dynamics are completely described by the generalized flux phi encoded across the junction. And this Josephson phase variable, which of course appears in the well-known Josephson AC and DC current relations, is by nature a coarse-grained variable and is also gauge invariant. That's because it is an integrated quantity of the integration here is done between the two superconducting islands of junction, and the integrand is precisely the hybridized gauge invariant field that I introduced in the previous slides. So, the core of circuit QED is coarse-grained and gauge invariant by nature. And this formulation can be thought of as just like a full generalization of the picture of this picture, and applies it to the entire discretized space that covers your entire device, not just the junction anymore. And yeah, so, and here I'm just showing like an example of a transmon capacitively coupled to a resonator, which is coupled to a waveguide. And the entirety of the structure is meshed during the simulation. And as you can see that in the close-up view, the junction loop, and that the hybridized field is encoded onto every single edge of your mesh, including the junctions. And you can also show the rigor of the approach by restricting the formulation just to, or reducing it to the 1D case, and show that this, discretized equation of motions reduces exactly to the standard transmission line circuit QED formulation that we all know and love. So it shows that, okay, at the limiting cases, it produces precisely what we hope that it would produce. And this is just like a generalization to full 3 plus 1D of that formulation. Right, so, and this sort of like framework very conveniently lends itself to a more general program that we aim for, which is the measurement adapted coarse graining. And that means, and that's because measurements, whether spatial or temporal, all have finite resolutions. And this is because your heterodyne detector has a finite resolution or finite spatial and temporal window over which it integrates the electromagnetic response it receives, right? So as a result, what is experimentally accessible to us, the measurement data that we receive are coarse-grained quantities by nature, which is what this formulation is trying to directly model. So the rule of the game here is just to try to simulate what you can measure and nothing beyond that, to save resources and at the same time maintain accuracy. Right. So with that point of view, it sort of makes a lot of sense to just directly develop a theory for these quantities, right? And the resolution of the simulation doesn't have to be, like I said, better than that of the measurement apparatus. And to really make this complete, we need to combine spatial constraining with time constraining, which is another ongoing project in our group. And we have opened up two public repos. It's still in its infancy. It's not as matured as many of the toolboxes that are presented in the workshop here. But it's hopefully that it's shown that proofs of concept are achieved, and we plan to sort of like extend this to make it more readily usable. Yeah. So. Right, let's recap what I have told you so far. So we have an effective field theory formulation that couples electrodynamics with the order parameter describing the superconductors. We formulate the equation so that it describes gauge invariant hybridized fields. We then discretize it so that the new equations describe the dynamics of the coarse-grained variables. And we now put it to test with, first really simple examples. Here we have like just a time-independent simulations of a Josephson junctions acting like a source antenna dipole enclosed in a superconducting cavity. And as you would expect, the radiation coming out of the dipole would permeate space and eventually hit the boundaries of the superconducting cavity. And we've deliberately chosen the penetration depth to be quite long so that we can see the field seeping into the materials. And generally, it's what you would expect. And because, nonlinear response of the superconducting material is baked into the equations of motion at the semi-classical level, we can recreate or sort of like verify nonlinear dynamics, such as Josephson current in a very ab initio manner, like really do the time dynamical simulations of the Josephson effect. And here's like an example of that, where we show the current density in a finite size Josephson sandwich in vacuum that is biased by sort of like an external magnetic field generated by these two parallel sheets of charge. And you can see during the time simulation that the current the electromagnetic field eventually will reach or penetrate the junction from the two sides, and that generates a current that flows across the two islands. And you can verify numerically that this is precisely a sinusoidal dependence when you ramped up the current. So yes.
This toy model, is the input to that like a mesh file?
Yes, it's the mesh.
Is there a certain structure to the mesh file for it to work with the package?
So right now it works with just DGS or GMesh, and you can just load it in and run the simulations.
In this case, you have some volume, some surface.
Mm-hmm.
Are you assigning any like ports to the mesh file? You need to have the information about what surfaces you want.
Yes, so it needs to know that your surface is yes. So you need to know to tell the simulator knows like this is like a metallic vacuum surface, for example, and you need to know give it like the material properties of your structures, and yeah, and right now we have only incorporated dielectrics and superconductors, which is sort of like all you need. But there's also plans to include quasi-particles into the model. Yeah, you can do that as well, or you can just like put in by hand, like you want, this surface to, or this material to have dielectric epsilon equals something. Yeah, right. Yeah, so you can simulate Josephson dynamics and verify that it's indeed a sinusoidal dependence. Sounds very simple, but it's a good test of your to see whether it captures the nonlinear dynamics of the materials. And you can also simulate other effects such as the Meissner effect, which is of course the decay of magnetic field as it enters a superconductor due to surface current screening, essentially. And here we just demonstrated that by having a superconducting bulk with a current loop wrapped around it that has a current, generates a magnetic field, and you can see in the simulation that the current inside the bulk decays according to the Josephson to the penetration depth. Yeah, which is what you would expect. There's also flux quantization, right? It's always fun to see flux quantization being realized. And this is sort of like a fundamental phenomenon in multiply connected superconducting objects, right? And so here we just demonstrate that by ramp current in the solenoid and observe the magnetic flux in the area bounded by the superconducting loop that contains a Josephson junction slit right there. And this is sort of like the real-time dynamics of the current density as you see it there. Yeah, it's the real-time dynamics of current density inside the superconducting object. And as everything happens, and you can, and also another way you can introduce magnetic field is, of course, it's just me playing with different geometries. Another way you can introduce fluxes is that you have your source to be placed side by side, and then the flux line will pierce into the second loop, and you should expect that flux quantization is respected. Right, so so I showed you that we can simulate the dynamics of how the material responses to the ramping up of the externally injected flux, so that the total flux that threads your loop has to be integers number flux quantum, right? This is kind of nice, but because I guess typically when flux quantization are discussed, we often just fall back to the static explanation that one would draw a line loop across the whole and argue that because the order parameter has to have unique values every space, every point in space, the superconducting phase around the loop has to be integers values of 2 pi, but we and hence flux is quantized, but the actual dynamical process of how that actually happens, it's usually not very clear or discussed at all. And so here is just like a way, just to show that you can really simulate the time dynamics of how this process happens. And the mechanism of it is actually quite fun, actually. And it turns out for this particular setup, where you have a superconducting loop with a Josephson junction slit, tiny over there, then the flux quantization is sort of facilitated by the creation and movement of vortices, actually, around the junction strip. And this video already kind of like illustrate that or hints at what really happens if you pay attention to the sort of current around the junction area. This sort of like switching back and forth of the current near the junction area is an indicator of local magnetic vortices being created and transported from the inner boundary to the outer boundary of your junction loop. So every time you have a vortex created over here due to the penetrating current, you create a vortex, and because of the Lorentz force, it's being dragged across the junction. And as soon as your vortex exit or enters the other boundary, your total flux inside this loop would, be added by 2 pi or minus by 2 pi, depending on the orientation of your vortex. So it's just, quite fun to be able to really see that happening in your numerical simulator. Right, so those were, time simulations. But how do we obtain the modes of the system, right? So when the response of the materials is taken into account, the problem, as you can see, becomes nonlinear. But if you're interested in, for example, the radiative profile of the device when certain modes are activated, then we need a way to analyze the spectrum. And the spectrum is then defined by just linearizing the equation for the hybridized field A. And through DEC, we arrived at the equation for the cosine field that lives on the edges. That which you can solve for the modes. It's a linear equation. You can solve for the eigenvalues and extract quantities like relaxation rates or hybridization, etc. So yeah, I'm just going to show some of results. First for the closed modes, so no radiative losses whatsoever. These are all closed objects. Then the system on the top here is just a simple 2D quarter wave coplanar waveguide placed on top of a dielectric substrate, covered by an air box. You can capture all kinds of modes, and we also have an example of like a 3D architecture where a 3D cavity contains 2 qubits mounted onto separate substrates. Here are some examples of like a qubit 1 mode, qubit 2 mode, 2 qubit mode, or hybridization of the cavity mode with the 2 qubits. So everything is sort of like captured. So those are closed modes of the system, but in reality, any system has some leakage, and every system is technically an open system, which makes the problem a lot more interesting, or also a lot harder. So therefore, being able to sort of like capture or account for the openness of the system and account for radiative properties of the system is quite crucial in modeling. And here we propose one approach to implement open boundaries, because you want to contain your simulation model to just a finite boundary. Because of course you have limited resources simulation. And the idea is that we like to sort of like limit it to be as tight as possible. So an imaginary boundary that contains all the components of the circuit and nothing else. And it sounds a lot easier than it actually is, because we typically don't know how the radiative profile escaping an arbitrarily shaped boundary. And so one way to formulate such a boundary is through the Green's theorem, because it allows you to propagate the solution from infinity, where the field is just plane waves, towards the finite boundary near the system of interest. And just to make sure that everything works, we applied it to a very simple example, which is just a radiated modes of a circular dielectric disk, which is a problem that has analytical solutions that you can directly compare with. And because the system is open, the spectral problem is essentially non-Hermitian. And the modes, instead of having real eigenvalues, the eigenvalues are now complex valued, with the real part being the resonant frequencies of the modes, and the imaginary part is precisely the radiative loss rates of those modes. So very conveniently, you obtain the loss rates very quantitatively without the need for perturbative analysis. And here we just overlay numerically computed solution eigenvalues on top of the analytical solution to show that accuracy is achieved even for very high order modes. You can also, of course, visualize the solution, and they are just Hankel functions in 2D. So they have very known profiles, and they're exactly what you would expect. So which gives confidence. Generalize it to a vector problem, because essentially that's what we're interested in. You apply it to the same geometry for sanity check. Right. So right now, so those were like, really simple examples. We can try to, apply it to a slightly more sophisticated example solution. Here we consider a, rather strange design where you have a qubit placed in like a narrow slit between two big cylindrical superconductors, superconducting bodies that act like a cavity containing the qubit, but it's an extremely lossy cavity. And because it's, widely opened, so radiation can easily escape. And we just took this really extreme case to demonstrate the ability to impose open boundaries very efficiently. Yeah, and here I'm just showing two examples of the possible modes of this open system. Yeah, so the mode shown on the top is just like a dipole-like mode where the qubit acts like a dipole with the field lines just, connecting the two islands. You can also have a high order modes where the individual superconducting islands act like their own monopoles with the field lines just, instead of, connecting the two islands, they just act like two separate islands. But you can only see this for high frequency. Yeah.
So question online, what are the assumptions made about the superconducting material that matter, Knowles order, single speed?
Yeah, so yeah, good question. So right now, because it's an effective field formulation, the superconducting the material's properties are encoded through penetration depth and the density of quasiparticles into your Schrodinger equation, basically. So yeah, the formulation works with, you can apply it to a geometry that has arbitrary number of different materials, as long as you know the London penetration depth and the density of quasiparticles in each of the materials. Yeah, hopefully that answers the question. Right. In both of these cases, you can see that, and also in other modes that are being computed, the openness of the system is sort of fully respected and captured. And the field, enters and exits your computational domain without any artificial reflections or discontinuity. And if you perform a frequency scan on the bottom left there or right there, then by varying the qubit frequency, which in turns vary the qubit frequency, then the qubit, and as the qubit frequency approaches the cavity mode, we will see very strong hybridization between the cavity mode and the qubit mode, and this sort of results in the very high radiative loss, or finite but high radiative loss, as captured by this finite peak in the imaginary part of the eigenvalue that corresponds to that cavity mode. And of course, you can compute kinetic inductance, which is the measurement of the inertia of charged carriers in the materials. And kinetic inductance, therefore, is directly related to the kinetic energy of the charged carriers. In the context of superconducting materials, those are the Cooper pairs. And because we have charge density, or the evolution of charge density being encoded into our formulation, you can very easily compute the kinetic energy of all the charge carriers through this framework. And then from there, extract kinetic inductance. Right, so here's just like a very simple TAR example of how to calculate kinetic inductance of a superconducting thin film. And if the film is infinitely wide, and then analytical solutions, of course, exist. And we, again, use it to compare with our numerical simulations to verify the accuracy. And yeah, but in most cases, you have to do it numerically. And an example of how you would do that is that if you want to simulate something that's like a microstrip line placed on top of the substrate, this is like, just a simple model for that. You would mesh the thing and solve for the linearized equation, which is just a Helmholtz equation. And the way I do it here is that you supply a current into one of the sides of your thin film and have it exit the other, which result in this equation that has a source on the right-hand side. And you would solve for this, solves this equation for the A field, compute the total kinetic energy of the entire system, and then extract the kinetic inductance very conveniently. This is how it looks like when you actually do it. Yeah, so just a linear problem to solve for. Yes.
Interfacial dielectrical loss tangent and participation ratios between the thin film and the substrate.
Yep, I was just gonna go to that. So very nice. Right, so in the last that's a slide. I'm just gonna try to show the calculation of surface dielectric losses, which in recent years have been a major source of study, because it turns out that this is one of the main culprit in limiting coherence of your system, right? And these losses come from thin layers, like the person just asked, from thin layers of oxide that appear at material interfaces and can be quantified by computing participation ratios. So essentially, the electromagnetic energy stored in these very thin layers of oxide appearing at interfaces of every two materials, right? And so properly modeling surface loss is, of course, very computationally expensive. And I'm sure who actually have to do it knows that how expensive it is, because these oxides are typically only a few nanometers thick, right? So whereas the rest of your structure is many orders of magnitude larger than that. Therefore, typically in these layers, in your simulation, these layers are removed from the E&M simulations. The participation ratios are then computed by sort of like apply post-calculation boundary conditions, right? So you first remove these really thin layers, do your E&M simulation to get the field profile, and then account for their existence by some sort of like ad hoc boundary conditions. Right. But I would try to show that this might lead to some underestimation of ratios of energy being stored in these layers. And that has to do with, singular fields appearing at dielectric corners. We all know that at metallic corners, there are singular fields, but these, fields, locations where the amplitude of the electric field, becomes extremely large, but they could also appear at dielectric corners. And because oxides are dielectric, if you remove them from the model, then these singular behavior that appears at the corners of dielectrics are no longer captured, right? Because you remove them. You only capture the metallic corners, not the dielectric corners. And like here's a picture of it that I just draw of the basic coplanar waveguide interface or cross section of that. And here's like a picture of the electric field in the structure, right? That's the electric field in the electrostatic simulation. And the field is obviously concentrated a lot around the corners. Right, and if you try to calculate participation ratios, here on the left, I'm showing the results for participation ratios of 3 types of oxide that, as function of the depth of the trench. The trench depth of your coplanar waveguide. So you have these gray area over there are the metallic components, and then I'm just plotting the participation ratios of the three types of oxide interfaces as the function of the depth that you trench your device. And you can see that in the middle here, it's the same calculation, but with the oxide included into your E&M simulation. In particular, you might notice that the result for the metal-air interface are quite different between the two plots. They're still the smallest, has the smallest contribution to the participation ratios, but there's obviously a significant difference in terms of like absolute values there. So you might risk underestimate their contributions in extreme cases. Yeah, so I am almost out of time, so I'm just gonna go quickly. Actually, I don't have much left. So yeah, so this is a crude demonstration to show that you can also use the method to model package modes and how they hybridize with the on-chip modes. And yeah, so you, again, here is a coplanar waveguide. This is the cross-section. And if you surround the waveguide and substrate with your metallic case, you have a multi-scale problem to work with. And here's just like a simulation or demonstration of how you might do that. So the entire, region here is the cross-section of the box. And this tiny, bright dot here, when you zoom in, is actually the coplanar waveguide being, placed in the middle. And that's the field profile. If you want to compute the modes of this, box that contains a coplanar waveguide, this is how it looks like. These are the package modes. And so the modes of the box, and this is like the waveguide mode, so to speak. And you have the waveguide being placed right here and here. So you can already see that in cases where, there's a node in the, or there's a maximum in the profile of your box mode, that overlaps with the location where you put your coplanar waveguide. You have really strong hybridization between the two, so it's very important that we're able to account for these sort of hybridizations because they might affect how the qubit mode looks like. Because in reality, everything is hybridized. I kept saying qubit-like mode and cavity-like mode because they're coupled to each other. When you do simulations, the presence of one in the electromagnetic environment of the other strongly modifies the mode profile. So there's no actual qubit modes. Everything's sort of hybridized. Yeah, so I think that's it. Just wanted to thank the team, my PI, Hakan, and thanks for listening.
Question? Do you expect that the computational overhead is going to be?
Yes and no. So I guess the main difference here is that we care more about how to correctly capture this so-called coarse-grained fields as opposed to standard finite element analysis, where you try to extract as much accurate solutions as possible. And sometimes you don't actually need them because in many cases, what you really care should be what's the resolution of the output port, for example, because even if you're able to simulate very extremely accurately, what you actually have in your measured data are doesn't live up to the accuracy of the HFSS simulation anyways. So why take the extra effort to do that? Where this is trying to sort of like model the actual dynamics and behavior of the coarse-grained fields that you have during your measurements. It's like slightly different. But if you really want to compare finite element with DEC, it's you can do it, but it's never fair for both of them because the object types are different. We can, once you do the simulation with finite element, you can sort of like try to map them onto discrete spaces and do the comparison. But by doing that, you already do some interpolation that reduces the accuracy of finite elements. And the same goes the other way. So it's just like two different sort of like paradigms, so to speak. Yeah.
Are there any losses from an air bridge that could be simulated in a similar approach?
I think so. Yes. There's no reason not to. Yeah, it should be possible.
Anyone first? Have you tested the model on lower dimensional quasi 1D, 2D superconductors?
Can you elaborate what's quasi 2D superconductors? Like,
I think you with quasi just means duplicate.
Oh yeah, yes. So you mean like, just simulate the one dimension? Yes, yes. Right, and actually we've just put out an archive that directly deals with 1D simulations, where we show that this formulation can be extended to the constraining nature of the problem can be extended to a time domain as well. So you have a space-time constraint lattice to work with, and we showed that you can very accurately simulate things like Sine-Golden models that describes 1D long-Josephson junction dynamics. That's one example of such dynamics. Yeah, so the short answer is yes.